Today, we're exploring experiments. Welcome to this explainer, where we're going to dive straight into some seriously fascinating fluid mechanics. Today, we're exploring Experiment 7 from the Uttara University Open Channel Flow Laboratory Manual. And our main objective? We are investigating this incredible phenomenon known as the hydraulic jump, covering the basics, the experimental setup, the calculations, and the whole shebang to figure out exactly how it dissipates energy. To really put this into perspective, think about this for a second. How in the world do we prevent the sheer destructive force of rushing floodwaters from completely washing away massive concrete dams? I mean, when millions of gallons of water spill over a dam, the kinetic energy is absolutely staggering. If we just left it unchecked, it would literally scour the riverbed and undermine the entire structure. There'd be nothing left. The brilliant solution? We intentionally create a controlled, violent collision of water. Here is our roadmap for today. 1. The hydraulic jump concept. 2. Real-world engineering uses. 3. The experimental setup. 4. Measuring the jump. 5. Crunching the numbers. And finally, 6. The final curves. Let's get right into Section 1, the hydraulic jump concept. So what actually is a hydraulic jump? Basically, it happens when a fast, supercritical flow, which just means water that's shallow and moving really rapidly, abruptly changes into a slower subcritical flow, where the water is deep and sluggish. Think of it like a massive traffic jam, but for water. Imagine fast-moving cars speeding down a highway, that's your supercritical flow. Suddenly, they hit bumper-to-bumper traffic, your subcritical flow. The result is this abrupt pile-up. In fluid dynamics, this conflict between upstream speed and downstream resistance resolves itself through a chaotic, tumbling rise in the water level. If we break down the anatomy of this pileup, you have your starting point where the fast initial depth, known as Y1, comes rushing in. It absolutely slams into the slower-moving water ahead, and that forces the water surface to rise rapidly to our sequent depth, or Y2. And that tumbling chaos right in the middle, that's called the roller. That is exactly where all that intense kinetic energy is being burned off as heat and noise. Moving on to Section 2, Real-World Engineering Uses. Now you might be wondering, why do we care? Well, this seemingly chaotic pileup of water is actually a heavily engineered tool. First and foremost, it dissipates excess energy over dams, weirs, and spillways. By forcing a jump to happen, engineers basically drain the water's destructive power, which stops it from destroying the riverbed downstream. But it doesn't stop there. This phenomenon is used to maintain high water levels for irrigation. Plus, that intense turbulence, it's perfect for rapidly mixing chemicals in water purification plants. And it massively increases aeration in wastewater treatment. It's essentially nature's very own heavy-duty mixer and shock absorber. All right, Section 3, the experimental setup. Let's see how we do this in the lab. To study this jump safely indoors, we use a horizontal rectangular flume equipped with a sluice gate. Water is pumped from a reservoir toward the gate. By lowering that sluice gate into the flowing water, we force the water to squeeze underneath it at a super high velocity. This gives us our artificial supercritical flow. As this super fast water travels down the flume and hits the slower moving water, which we control with a downstream tailgate, boom! We induce that fast to slow water collision right before our eyes. Which brings us to Section 4, Measuring the Jump. The lab procedure here is actually beautifully systematic. First, we take a point gauge and measure the initial depth of the fast water, Y1, right before the jump kicks off. We actually take 3 separate measurements and average them out just to be super accurate. Then, we do the exact same thing downstream to get our sequent depth, Y2. Next up, we measure the physical length of the jump itself, so from the front face to just past that turbulent roller. Once we have those physical dimensions, we transition over to the calculated metrics. By knowing the discharge rate from our water meter, we calculate the upstream and downstream velocities, and that allows us to determine a very special metric, the Froude number. Let's dive into Section 5, Crunching the Numbers, and solve this math mystery. Comparing our before and after states reveals a pretty dramatic shift. If we look at the demo data from the lab manual, our initial depth, Y1, was just 4.1 centimeters. But it was rocketing along at a velocity of 91 centimeters per second. After the jump, our sequent depth, y2, swelled up to 9.2 centimeters, while the velocity plummeted to just 41 centimeters per second. The depth more than doubled, and the speed was cut in half. The jump absolutely did its job. But we need to know, exactly how violent was it? To answer that, engineers used that upstream Froude number we mentioned, labeled as F1. It's a dimensionless parameter comparing the water's inertial forces to its gravitational forces. The United States Bureau of Reclamation categorizes hydraulic jumps into 5 distinct types based on this exact number. If F1 is between 1 and 1.7, it's an undular jump, super mild. But if that Froude number creeps up past 9.0, you are looking at a strong jump, which is incredibly turbulent and highly effective at bleeding off energy. So, what was the Froude number for our specific lab demonstration? Using our initial velocity and depth, the math reveals an upstream Froude number of exactly 1.43. Connecting that 1.43 directly back to our categories completely solves our data mystery. Our lab experiment successfully generated a type 1 undular jump. Because our Froude number was sitting right between 1 and 1.7, the resulting water surface just showed some slight undulations, rather than a massive plunging roller. It's literally the gentlest form of a hydraulic jump. It's perfect for a safe laboratory demonstration, but make no mistake, it's operating on the exact same physical principles as the massive roaring jumps at the base of the Hoover Dam. Finally, Section 6, the final curves. These characteristic curves are where we turn our raw data into a real, predictive tool. Notice the curve representing E2 over E1, that's the energy efficiency of the jump. See how, as the Froude number on the bottom axis increases, that line slopes downward? That perfectly illustrates that the stronger the jump, the less energy remains downstream. By plotting these values, civil engineers can visually predict exactly how much destructive kinetic energy will be safely dissipated for any given flow condition. This is how they design spillways that perfectly match the demands of a river. It is truly amazing to think that something as chaotic and violent as rushing water can be mathematically predicted, controlled, and utilized. By turning extreme danger into a mechanism for safety, civil engineers master natural fluid dynamics to probably. How might harnessing this chaotic force inspire?
जी सर। স্যার, কোড নাম্বার যদি একের কম হয় তাহলে তো এটা সুপার বিটি করা হয়। কোড নাম্বার একের সমান হলে সরি, কোড নাম্বার একের কম হলে সাব ক্রিটিক্যাল, আর যদি একের সমান হয় তাহলে ক্রিটিক্যাল, আর একের বেশি হলে সুপার ক্রিটিক্যাল।
জি না স্যার।